Take a look at this picture and this picture. They're both drawn very differently, but we're able to see them as the number 2. Now, even though the specific light-sensitive cells that fire in our eyes from looking at each image are different, our brain can still see them as the same number. But a computer, on the other hand, would find it difficult to do this unless it had some kind of artificial brain to mimic what our brain does. And this artificial brain is called a neural network.
Similar to the brain, neural networks are made up of several neurons, separated into layers, that each carry a number from 0 to 1 called an activation. These neurons are connected to each other by weights, which are just numbers.
And by choosing a certain combination of weights, we can make our network do many things, like identify handwritten digits. Now, to input an image to classify, we match each pixel in our image with a certain neuron in our first layer, and make that pixel's grayscale value equal to the neuron's activation.
Now, we can calculate the activation of a neuron in the next layer, called a hidden layer, by adding up the products of each activation and weight connected to it, and squashing that big number by putting it into the sigmoid function, so that it's between 0 and 1 based on how negative or positive it is.
And we'll also add a bias term that will act like a threshold this sum needs to pass for the neuron to be meaningfully active. Now, in the last layer of our network, we have 10 output neurons that each represent a number from 0 to 9. And once we calculate the activations for every neuron in our network, the output neuron that clearly has the highest activation will indicate what the network thinks the number we showed it is. But this guess will only be accurate if we choose the right weights and biases. And since there can be thousands, if not millions of them in a single network, we'll help the computer choose them through a process called training.
We start by randomly choosing weights and biases, and then input an image, like this 8, and see how the network does. Obviously we'll get a bad output, but we can measure exactly how bad it is by comparing it with the output we wanted and calculating a cost based on the difference. The higher the cost, the more inaccurate our network is.
And once we take into account the costs of thousands of other example images, we can create a cost function with weights and biases as inputs and a single cost as an output. Now, to minimize this function, we use calculus to see what small changes to our initially randomized weights and biases will decrease our cost the fastest. This process is called gradient descent.
Let's start by thinking of it as trying to get to the bottom of a hill with our eyes closed. Even though we can't see the bottom, we can use our feet to figure out which way to step to move downhill the fastest. This direction is called the negative gradient. Now we can repeat the process of finding the direction of steepest descent and taking steps in that direction until we finally reach the bottom of the hill. Similarly, we can continually tweak our weights and biases in the direction of the negative gradient of our cost function until we can't decrease our cost anymore. Now, with our cost as low as it can be, our network can accurately identify handwritten digits it's never seen before.
But this is only the beginning. Engineers have made more complicated neural networks that can make self-driving cars see and help scientists fight cancer. But even these innovations are still quite recent, and with a few more years, who knows what we can teach computers to do next.